In this example, we made assumptions about taking limits that ended up with some result. We learned that fields can be represented by their limits for certain situations. In one situation, we saw that in the limit as L was much, much bigger than Y, we could take the result of the finite line and we replaced it with an approximate value for an infinite line. And the other situation that we looked at is that if I took the limit where Y was much, much bigger than L, then we could replace the finite field at large distances with that of a point. So the question is, how good are these limits? We should calculate them. So I'm going to use the numbers that are given here. We have a charge, we have a length, and then we have two different values for Y. So in the first situation, we could see here that we're going to compare the length of 14.5 centimeters to 1 millimeter. So if I get really close to that line, it's going to look like an infinite line. So that means, can I replace that? So let's look at the first case. In the first case, we want to compare E finite versus E infinite when L is much, much greater than Y, right? That's what we want to do. We want to compare them. So let's go ask that question. Is Y really much, much bigger, excuse me, much smaller than L? So if L is much, much greater than Y, we should see this. And the way we see this here is that we calculate a ratio. So the ratio in this situation is then going to be Y over L. And if I put in the numbers, if this is 1 millimeter, this is 145 millimeters, which means then that this is 0.0069. And you could see that that number is really small. So that's telling us that it should be a very good approximation. So now let's numerically calculate these fields and compare them. So I know that the field of a finite line looks like this. So the field of a finite line was 4 pi epsilon times y divided into q. And then I had the expression of y squared plus 1/2 L squared square root, and that goes all into 1. So I'm just going to take the values that we have. So the values that are given in the question here says that Q is equal to 7.81 times 10 to the minus 12 coulombs. Y is 0.001 meters, and L is 0.145 meters. So I'm going to assume that these digits are exact. Okay? If the digits are exact, then I'm going to say that then I'm going to get something like this here. So if I look at this thing numerically, then I have to talk about 1 over 4 pi, which is then going to be 8.99 times 10 to the 9, and this will be a Newton meter squared per coulomb squared. Then my charge here is 7.81 times 10 to the minus 12 coulombs divided into 0.001 meters. And then I have, of course, 0.001. In fact, I'm going to drop the units here for this. And then this should be 1/4 times 0.145 squared square root all into 1, and this will give me units of meters. So if I start to cancel things out, you could see that the meters are going to cancel out. I look at the charge, and I see that one of these charges cancels here, and that cancels. So that gives me units of newtons per coulomb. So if I compute this number, this is what we get. We find here that the number is equal to 968.322 newtons per coulomb. And this is going to be E finite line. You know that? That better not be, I'm pretty sure that's a correct number. Now, let's do that for the infinite line now. So now I have the infinite line result. And when I look at this thing, I see that this guy is actually equal to 2 pi epsilon y. And then this is then going to be 2q over L, which is the charge density. Now, wait, let me be careful here. That 2 is not there. But I think that we should put a 2 here. So if I multiply and divide by 2, then I have the result of 4 pi epsilon. So let's do that. So then if I do that, look what happens. I'm going to change this. So I'm going to add 2 here, and I'm going to put 4 there. So now I can numerically put in these values. Now note, we have everything from above. So I'm just going to put in the numbers, and I'm going to drop my units here just to be fast. So this will be 8.99 times 10 to the 9. Then I have 2 times the charge, and the charge here is 7.81 times 10 to the minus 12 coulombs. And then the length of this is 0.145. There's my charge density. And then finally, my distance here is 0.001. So if I compute that, I'm going to get a number that then reads 968.440 newtons per coulomb. And this is the field of an infinite line. So let's compare these results. So one of this is what we actually integrated to get this guy right here. And if I look at this guy, I have this. Now, if I was to round properly, because I set my 1 over 4 pi epsilon, my k value, to 3 sig figs, so that's 8.99. So to 3 sig figs, you could see that they're exactly the same. So to 3 sig figs, the approximation of the limit as L is much, much bigger than this for the E field of a finite line is exactly the same as the infinite line approximation. It's a valid uh, conclusion, right? So this is clearly a valid statement. Now, if we wanted to go to more sig figs, we'd have to, again, start adding more sig figs to the k value. Now, let's look at the next one. So the next one looks something like this. So up here, we said that it says, let's compare these two fields when y is greater than smaller than L. Now we're comparing these fields right here, the finite line and the point thing. So here we go. So we want to compare the field of a finite line. And in this situation, we're picking y to be much, much larger than L versus the field of a point. Now, what's different here is that the values or the value of L is now L equals to 5. Nope, not L. Y is now 5 meters, but everything is the same. So again, is this a good approximation? So as we said before, we're saying here is that y is much, much bigger than L, but that's not how we write it. We write it as the ratio of L over y. So in this case, the length of the finite wire is now being compared to 5 meters out. So if I compute that, this is 0.029. And I would say that, again, this is much smaller than 1. So it should be a good approximation. So let's calculate these fields. So calculating these fields, we see the following thing. Now, the field of a finite line is the same only with a small change. So I'm going to come over here and I'm going to copy this, because the only thing that's changed here is only the value of, where did I put it at? It's only the value of y that has changed. So that's the only thing we have to change here. So if I do that, then this is what I'm changing. This here is now 5 meters. Since we've already done the calculation, I'm not going to do it again. I'm just going to say I'm going to punch everything in, and this is what I get here. I get that this field is 2.808 millinewtons per coulomb. So remember, so this is a small value. And it should be small because we're far away. So this guy is the field of the finite line when y is much, much bigger than L. So this is a value that we need to compare to the point field. So if I look at the point field, it now looks like this. So the E of a point field is of course equal to 4 pi epsilon y squared divided into q. So because this is a new calculation, I will do it. So this will be 8.99 times 10 to the 9. Remember, I'm dropping the units. And then my charge here is 7.81 times 10 to the minus 12 coulombs divided by the 5 meters squared. So if I compute that, I get a value of 2.808. Actually, this is 1 and this is 5 millinewtons per coulomb. So if I look at this, this is the field of a point. Now here, remember, this was only good to 3 sig figs. And you could see that for 3 sig figs, they're exactly the same. The field is then going to read 2.81 millinewtons per coulomb. That tells you that the assumption that the field of a finite line for y much, much greater than L is equal to that of a point. It's a good assumption, is valid.